So we're going to start off part 6 with the implementation of the diffusion operator. Now I'm going to take that step by step because I think there's a lot in here, and I want to make sure that I get that right because I think that's the important part. So and I'm curious to know and to see whether this is going to be somehow related or an adaptation that's based on one the way the oracle is implemented, but I doubt it because that would be kind of against the purpose of Kerber's algorithm, where you shouldn't really care about the oracle. So that's a major thing that I'm curious about. It's like there's a trick. So there's a bit of a here of emphasis put on how to build the oracle so that it runs on disk machines with this trick of the subdivided phases, and so I want to see how much this amplitude amplification really depends on that, because I guess part of the advantage of having those two things separate is that you can basically reuse the amplitude amplification for other things. So let's see how much those are tightly coupled. And especially the fact that because you have subdivided phases, this means you're not gonna have a 180 degrees phases, which kind of it's what's used in the ideal Grover's implementation, right? That remember that the subdivided phases had the issue that both the worst solutions, like the ones that are like 0, 0, 0, so like all zeros or all ones, they're also enhanced. Their amplitude is also enhanced. So you're not just amplifying the amplitude of the right solutions. So let's see what happens. Good. And so I'm even thinking it's not a super long section, but I might even do this in 2 parts. I haven't really read that through, so we'll see. And then the next is experimenting with IBM-Q devices, which I'm probably gonna do along the way I also do the other series on the Qiskit, on the Qiskit textbook, because I think they just will play together very well, and then we'll get and then we'll just go back and dive into the details that we kind of went through or kind of glossed over in the previous videos. Good. Let's get started with these. So implementation of diffusion. After executing the oracle in section 4a, we perform the normal diffusion operator for Grover's algorithm. As described in section 2, the diffusion circuit for n+1 data qubits require an n-control NOT. Therefore, we discussed how to implement an n-controlled X-gate under the constraints of the IBM Q processors. So, the standard way to implement the amplitude amplification is the following. So, the standard way, right? So there's other ways you do this. You could do this based depending on how your initial state looks like, but you would basically have a bunch of Hadamards, say for 3 qubits, right? And then you would have a bunch of X gates, and then you would have a controlled. I think you've got another Hadamard in here. Exactly, because this is a control Z, and at the end of the day, that's how you would implement in a class, like the typical. That's how you would implement the typical thing, right? So if I would now say I want to phase, and this is the amplification, I'm just gonna make a really simple oracle, just to test that it's correct. So this is gonna. So first we'll get into superposition, and then we'll basically drop in. So so we're gonna drop in this control Z, which basically flags that 0, 1, 1 state. So that's the one that we want to amplify. Correct. Is that correct? Oh yeah, we also have flipped now. So we also have flipped the 1, 1, 1. So we've got 2 flips, two flipped in here. So and what the amplitude amplification is going to do is going to basically exactly those ones. They're going to get like the amplitude amplified, and everything else goes away. So this is the way it works. So that's why the paper says you need a control like X-gate. Effectively, this is these, right? So You could also do it this way. I still struggle to understand why they stick to control X gates. Is it the control Z is not native somehow? Maybe that's the reason. I don't know. I'll have to dig into this probably, but that could be a reason. So, but that's this basically. So okay. So and of course you're gonna have some constraints because I'm assuming that the chips might have some specific connectivity. So this means you can't just do control gates across all the qubits. So you might have to, they might not all three be connected physically. So you might not be able to implement that straight away. So that's figure 8. That was from the previous section. Control X gate implementation. To construct the control X, we introduce the relative phase Toffoli gates Artoff. So wait a second. The relative phase Toffoli gates. What are the relative phase Toffoli gates? A Toffoli gate is known to require 5 controlled unitary gates or 6 controlled X gates. But Artoff works almost like a Toffoli gate, requiring only 3 control X gates. In compensation for the reduced number of control X gates, an undesired phase is added to the target, which must be compensated later. We adopt 2 types of Artoff, shown in figure 9. Both of these Artoff can be implemented on a system with only a one-dimensional qubit layout, whatever that means. Although the number of controlled X gates is equal, Artoff sub IX does not require U3, which reduces single qubit rotation errors. We also introduced the Toffoli gate with built-in swap operation. Toffoli gate implementation with the minimal 6CX gates requires 3 qubits interconnected in a triangle. Recent IBM Q devices after IBM Tokyo do not have a structure that can embed triangles. To deal with this situation, we propose a Toffoli circuit. A Toffoli circuit suitable for a one-dimensional layout that is shown in figure 10. Circuit requires one additional control X gate. However, since swap is built in, it is necessary to consider the location of qubits in the output state. By using those components, we can configure a controlled X, an N control X gate for the recent IBM Q devices using 6n-5 control gates. It is known that N control X gates can consist of 2n-3 Toffoli gates with n-2 ancillary qubits initialized to 0. A Toffoli gate contains at least 6 can be replaced with an Artoff except for the central one to support additional implementations. We show the procedure for an n-controlled X gate in algorithm 1. Okay, so there's the algorithm. If the processor can embed the structure shown in figure 12, the procedure can be executed without additional swaps. Okay, there's a lot of stuff in here. Let's take it step by step. Kind of skim through this. I mean, first of all, what's Artoff? So we introduced the relative phase Toffoli gate. So what is this? So that's this thing. That's this here, right? That's the gate Artoff. Works almost like a Toffoli gate, requiring only 3 controlled X gates. In compensation for the reduced number of controlled X gates, an undesired phase is added to the target, which must be compensated for later. Okay, so it's supposed to work like the Toffoli gate, but it has an undesired side effect. Okay. What's that? That it adds an undesired phase? Is this because phase kickback or? Let's see. Let's focus on this maybe for this video. So, because it seems it's going to be, that's going to be. I want to make sure I understand that correctly. And so we can maybe take a look at clearing. Can I not zoom out here? gonna clear this out, clear all. So the Toffoli gate is basically this, right? So what you wanna do is have this effect of like when these are both on, then the chance of this being on is also 1. So that's one case. I mean, that's the simplest way to explain that. I guess if what you've got in here is a plus plus, right? What you end up with at the end is, that's interesting. So that's the of course the 1 1 1. So basically you get rid of, you get a superposition where you've actually gotten rid of the things that are impossible. So this would be impossible because the 2 qubits starting from the right side 1 0 don't satisfy the Toffoli. This don't satisfy the Toffoli, don't satisfy the Toffoli, doesn't, and this satisfies Toffoli, but then the leftmost qubit is 0. So that's an invalid element. So basically only this is going to give you a superposition that of elements that satisfy the either 1 1 1 or like 0 and then 0 1 1 0, right? So or 0 0. So that's a valid state, that's a valid 1, that's a valid 1, and that's a valid 1. Okay. Yeah, but you get what I mean. So the idea is how to implement that, because typically to implement that you would require, I think you basically got a Toffoli gate does not require 5 controlled unitary gates. So I think the idea is that if you would want to do something like that, you would have to do it with control knots. So you would have to do something like this, correct? Is that equivalent? So to construct a Toffoli gate does not require 5 controlled unitary gates for a 6 or 6 control X gates. So no, so you would do something like that. You would do something like that, and how would you implement that? So there's a reference here of 20 multi accumulator phase. How would you implement? So how would you decompose? So how would you decompose the Toffoli gate into a control NOT gate? So you want to have that case where if both are 1, this is 1. It's sort of an AND, right? So you would say if this is 1, flip this to 1. If this is 1, flip this to Z. Flip this as well. But then, I mean, that should be basic. I should be able to build that, decompose that quickly. So here, controls unitary gates. then we need to correct. Then we need to correct from the fact that we don't want, when those things are 0, we don't want this to be, because now I would say, you know, you could do something like that, and then that gives you the correct effect in here. For this case, it gives you the correct effect as well. In this case, it gives you the correct. In this case, it gives you the correct effect as well. But then this is, you want to correct for that, right? So you don't want these. So how would you go about it? Would you just basically say, well, if this is 0, come on, it can't be that difficult. If I'm not able to, if I'm not able to do that, then I would. Gotta take a slightly different approach, step by step, I think. So basically, if this is, so we're gonna do probably something like that. So if this is 1, then flip that. Or if this is 1, then basically flip that. Now if this is 1, you gotta flip that as well, but then, you know, if you flip that and it turns out this was a 1, then that'll be a 0 now, right? So but if it was a 1, oh yeah, okay, so if it was a 1, then you know, if it was a 0, then it's going to be a 1. So that gives me the chance to correct that and say, give me a second. So if does this work? So if this is 1, right? Then basically that would just activate this one here. I guess that's still wrong, so we need to correct for that by doing this. Is that correct? So if this is 0, so if this is 1, and this is 0, right? This is 1, then we activate that. That's kind of a target. And if this is 0, that's going to still be a 1. So that's going to get corrected automatically, and we're done. If this is a 1, nevertheless, we want that activated. So this is going to basically do. So this is going to basically say, okay, so this is 1. Toggle this one. So now we've got it on. If this is 1, toggle this one, which kind of will become 0, so it will avoid the correction. It will avoid the correction. But we still gotta. But we still gotta somehow correct, because now this is gonna jump in and mess up. So we still gotta do something like this. Is this correct? No. So okay, so basically this is 1. We want to toggle this one. Then with this one here, we're avoiding the correction. There's maybe another one in here. That gives us what we want for these. For a 0, 1, 0 is... No, that's not correct. Is it even doable? So you're basically... that should be basic. So I learned, yeah, so I'm basically learning that I don't even know how to decompose that. So I probably should better try to figure these out first and then try to understand these in here. Maybe it's not with control node operations, what you're doing is something else. Okay, I gotta figure this out first. Yeah, that was a short video. Okay, cool. That was a really short video, but it's yeah, I want to make sure I understand that first before I jump into the Artoff. So how I would decompose, how I would basically decompose that like that, and try to understand. Okay, so how does this implementation help us save uncontrolled X gates? Cool.